Welcome to the 31st lecture of combinatorics. In the last class, so we have seen that given a sequence H0, H1, H2 etc. Satisfying a linear homogeneous recurrence relation with constant coefficients and of order k, we can find a generating function of the form p of x by q of x, where p of x is a polynomial of degree strictly less than k and q of x is a polynomial of degree k and the constant term being equal to 1. Now, we will show that the converse is also true. Suppose you are given a polynomial some generating function of the form p of x by q of x, where p of x is a polynomial of degree less than k and q of x is a polynomial of degree k and having a non-zero constant term. We are not insisting that the constant term be 1, so we just want it to be non-zero. And then there will always be a sequence H0, H1, H2, H3 etc. such that this is the generating function, this is the and not only that, the sequence will be there such that it will satisfy a linear homogeneous recurrence relation with constant coefficients of order k, and the generating function for that sequence will be this one. Right, this is our aim today. Again I will repeat. So, we are given a generating function g of f, some g of x of the form p of x by q of x. And what are the properties of p of x? P of x is of degree less than k and q of x is of degree equal to k and its constant term not equal to 0. This is what we have, two conditions about p of x and q of x is given. Now, we say that we will show that there exists a sequence H0, H1, H2, H3 etc. such that it will satisfy a relation of this form Hn equal to A1 into Hn minus 1 plus A2 into Hn minus 2 plus Ak into Hn minus k. This is order k recurrence relation, and these coefficients are constant, and definitely this is a homogeneous recurrence relation, linear homogeneous recurrence relation. This is right. This is what we are going to show. So, we have to show that show the initial values H0, H1, H2, H3, Hk minus 1 can be found out, and also show that for the terms Hn where n is greater than equal to k. So, this relation will be true, this equation will be satisfied, right. This is what our aim. So, what we do is we just write. So, suppose there is one such sequence, then g of x has to be like this, right, h0 plus h1 x plus h2 x square plus h3 x cube and so on, right. So, we are talking about this hi's, right. If at all such a sequence exists, g of x has to be like that. So, our claim is that this g of x is equal to p of x by q of x, where p of x and q of x are given and have the properties mentioned before. That means we have So we can cross multiply. This is our g of x. So we can cross multiply. We get p of x equal to q of x into h0 plus h1 x plus h2 x square plus and so on, right. Now let us say this p of x is say d0 plus d1x plus d2x square plus dk minus 1 x raised to k minus 1, because we are saying that p of x is a polynomial of degree strictly less than k minus 1. So then let q of x be equal to say b0 plus b1 x plus b2 x square plus like that. So bk x raised to k. So here the q of x is a polynomial of degree k. So b of this bk is non-zero, and also we have the assumption that this b0 is a non-zero term, right. This is non-zero, b0 is non-zero, and also bk is non-zero. This is what we know. Now, so this is the equation. This is p of x, this is q of x, into we have the h0 plus h1x plus h2x square plus h3x cube and so on, right. Now what we do is we compare the like terms. That means the first we compare the constant terms. So the constant term here is this d0. So and here the constant term will be b0 into h0, right. There is no other constant term here. So b0, there is no other contribution to the constant term. So we get b0 h0 is equal to d0. This is first what we can write. b0 h0 is equal to d0. Now we can look for the coefficient of x. So the coefficient of x here is d1. So we write d1 equal to what? The coefficient of x from this side, from the RHS, the right hand side, is b0 into h1 plus b1 into h0, b0 into h1 plus b1 into h0, because here b0 is a constant term, here h1 has an x with it, h1x. So b0 h1x will come. Here b1 has an x, b1x, b1 has an x with it. So we have to multiply the constant terms of the second part, right, b1 into h0. That is what we will get. So b1 into h0 plus b0 into h1 will be d1. So these are the equations 1, these are the equations 2. So now we can compare the terms corresponding to the coefficient of x square. So d2 is the coefficient of x square. So d2 will be equal to what, right? d2 will be equal to b0 into h2, because b0 h2 will make it, and now from here b1 into h1, b2 into h0. So this will be b0 into h2 plus b1 into h1 plus b2 into h0. This will be d2, and like that we can compare the coefficient of each term. And you see, so you can write for the dk minus 1, that is the coefficient of x raised to k minus 1, this as b0 into h k minus 1 plus b1 into h k minus 2 plus like that. When we say b k minus 1 into h0, this will be true. So, this is the k minus 1th. So, these are so many equations. This is the k minus 1th equation. Okay. Now, from now on, what we get is, so for instance, when you consider the coefficient of x raised to k, what will happen? The coefficient of x raised to k is dk, that will be equal to, see, on the other hand, you should note that this dk is 0. Why? Because here this is p of x, it is a polynomial of degree at most k minus 1. So, dk has to be 0, right. So, this is 0, and then, so now you look for the coefficient of x raised to k from the RHS. So, from the RHS we will see that b0 will multiply hk and b1 will multiply hk minus 1 and so on. That is the way we get this thing, b0 hk plus b1 hk minus 1 plus like that. So, b k h0, this will be equal to 0. This is what we get. Now, from now on, everything will be like this. For instance, if you want to consider the coefficient of x raised to k plus 1, again it is 0 from the left hand side, because p of x does not have any x raised to k in it, because it is a polynomial of degree at most k minus 1. So, that will be again 0, but from the other side we will get b1 into hk what we will get is b0 into h k plus 1, because we are talking about k plus 1, and then plus b1 into hk, because you know this will in the first term b1x will come, hk into x raised to k, that will provide x raised to k, and like that. So, all the way to bk into, bk has x raised to k already. So, we have to take h 1, right. Bk has h raised to k, we have to take h1. But you see, you cannot get the next term, for there is nothing like bk plus 1 into h0. Why? Because this bk plus 1 is anyway 0, because our polynomial qk, this polynomial, right, q of x, sorry, q of x, this q of x was a polynomial of degree k. So, therefore, up to bk only we have here. So, bk plus 1 onwards is 0. So, therefore, this term will not be there. So, we will stop here, and this is equal to 0 is what. So, like that, for an arbitrary term, when you take the coefficient of x raised to n for n greater than equal to k, what we get is b0 into h n plus b1 into h n minus 1 plus, so bk into h n minus k is what we will get, right, because each term will give a contribution to the coefficient of x raised to k. But from bk plus 1 onwards we have 0, therefore, no more contribution, this is always 0. So, you can see that this b0 is a non-zero quantity, therefore, we can divide each term by b0. So, that means this b0 will disappear, and divided by b0 we can put here, and say here we have b2 into hn minus 2. So, divided by b0 we can put here. So, here also, so everything will become something like b, so 1 plus b1 by b0 into sorry. So, once again Hn plus B1 by B0 into Hn minus 1 plus B2 by B0 into Hn minus 2 and so on up to Bk by B0 into Hn minus k equal to 0 is what we get. So, this is the recurrence relation. This is, you can see that this is a recurrence relation of order k, and these are constant coefficients, right, and this is a linear homogeneous recurrence relation. The only thing is how, the only thing left is how we are going to get the initial values. So, this recurrence relation is valid for n greater than equal to k, as we have seen. How to get the initial values? These initial values are easily available from the first k minus 1 equations we have wrote first here. This is a triangular system of equations. For instance, you look at this, we know that this B0 is non-zero and D0 is given also, right. So, you can divide D0 by B0 and get H0. Now, once you get H0, so we know B1, so B1 into H0 can be calculated, this one. Now, D1 is known, so we take this part to the other side, that means B0 into H1 is equal to D1 minus B1 times H0. But this again, this B0 is non-zero, so we can divide by B0 and we will get H1. Like that we can get the values for H0, H1, H2 up to Hk minus 1, right. So, from there onwards we do not need the value because the recurrence relation is valid. So, as we have seen before, right. So, therefore, we have obtained a sequence H0, H1, H2, Hk minus 1, Hk, like that, right, satisfying a linear homogeneous recurrence relation with constant coefficients and of order k, and we found the initial values. So, that means what we have proved is, so if g of x is given as p of x by q of x for p of x any polynomial of degree less than k, q of x a polynomial of degree k and constant term not being equal to 0, right, then we can get a corresponding sequence for this g of x. This is what we have shown. Now, we will so we have not done too many examples, but for this we do not need too many examples because the method is very clear. It is always, so we have done the general cases and we have did a little some analysis of those the method, and we showed that how we can get a generating function always for a sequence satisfying linear homogeneous recurrence relation with constant coefficients and of order k, and reversely for a certain kind of g of x's, how we can make sure that, so it is very general that g of x we can make sure that there is a sequence, so that is the generating function, right. So, we just need a p of x by q of x form. Q of x has only the condition that it is of degree k and its constant term is non-zero. P of x is of degree less than k, that is all. So, we do get a generate sequence satisfying a linear homogeneous recurrence relation with constant coefficients and of order k, and such that this is the recurrence generating function for that. Now, our plan is to consider some slightly different kind of recurrence relations than what we were considering up to now, and we will solve it just for being familiar with it. So, these problems themselves are not very unfamiliar. For instance, let us look at the problem. Let us define a of n comma r be the number of ways we can select with repetitions allowed are objects from a set of n distinct objects. So, we have already seen this problem. We know that A of n comma r is n plus r minus 1 choose n, right. Sorry, r. So, n plus r plus n minus 1 choose r, that is what we have seen, right. So, and then now we want to get the same thing using the method of generating functions, just for a practice. So, though we already know it. So, this is, but then to use generating functions we have to, I mean the way we were studying generating functions as a tool to solve the recurrence relations, we would first have to come up with a recurrence relation for this A of n comma r. So, let us think about it. See, again A of n comma r is the number of ways to select r things from n different objects, different type of things or something, different objects. We want to select r things, but repetitions are allowed, right. So, we have studied this in detail before, right. So, now what we can do is we can write a recurrence relation like this: A of n comma r is equal to write the recurrence relation we consider like this. So, there are n objects, right, 1, 2, 3 up to n. Out of this n objects, let us consider this nth object, right, and if we decide to pick this nth object once, at least once, then you know that means that we have to select then r minus 1 more objects from the n objects. The repetitions are allowed because the objects will not disappear because I took this once, because the nth object is taken once, it is again available because repetitions are available, repetitions are allowed. So, therefore, once you decide to take n, the only we have to take r minus 1 more objects, but all the n objects are available. So, that is A of n comma r minus 1. The other case is when we decide not to take this at all, this object is not at all being used. That means we have only n minus 1 objects available. So, we have to take all the r objects from that. So, that is A of n minus 1 comma r. This is the recurrence relation. And now for what values, so fixing an n, so what values of r this is valid. So, we can say that this is valid for r greater than equal to 1, because so here let us say, yeah, n is, we will assume n is greater than equal to 0 of case, right. So, now if r is greater than, so one thing is very clear, if A of n comma r, if r is right. So, sorry, one A of n comma r. So, we are assuming n is greater than equal to 0. So, now so A of n comma 1, right. So, that means I want to take one object from n objects. So, if I decide not to take it, so we will get A of n comma 0. So, that has to be sorry. So, if you decide to take the that particular object 1 and n equal to 1 here, then that means we want to pick up 0 objects from n objects. So, we will decide, so we will write a n 1 equal to a n 0 plus the other thing is when I decide not to take it, right, then that is a n minus 1 1, right. So, this is so we know that a n minus 1 1. So, one object from out of n minus 1 you can take in n minus 1 ways, this has to be defined as 1 then, right. So, see intuitively, so what I am trying to tell is, so a n 1 has to be equal to 1, right, you know, because if you want to select one thing, one object out of available n things, repetition allowed, because anyway repetition does not make much sense because we are taking only one object, right. So, the answer has to be n here, right, because there are n ways of selecting it. Now, if I want to make the recurrence relation true, so a n 1 is equal to a n 0 plus a n minus 1 1. So, this should be n minus 1 plus this has to be 1, right. So, a n 0 should be defined as 1. That means, when I am thinking of selecting 0 objects with repetition allowed from out of n, we should define it as 1. So, we have a n 0 is equal to 1. This is one thing. Now, where will you start? For instance, what about so we will design as decide that this recurrence relation is true for all n greater than equal to 1, for n equal to 1, sorry, for all r greater than equal to 1, for all r greater than equal to 1, this is true. For if you put a n 0, then we will have to define something for a n minus 1 also, that we are not going to do. So, therefore, we will say that this is valid only for r greater than equal to 1, right. So, once again I will write the recurrence relation a n r is equal to a n r minus 1 plus a n minus 1 r. This is true for r greater than equal to 1. Now, we will define some generating functions for this sequence. So, what about a n 0? So, consider this sequence a n 1, a n 2, a n 3 and so on. You remember this is defined to be 1 and this will be n and like this, right. This sequence will give rise to the generating function, say let us write it as f n, because so this n becomes the parameter in the generating function. F n of x is equal to sigma r equal to 0 to infinity a n r into x raised to r. This is the generating function. We start from 0 onwards, right. So, we have to, so we know the f n is defined for n equal to 0 onwards. So, for instance, what will be f 0 of x? F 0 of x. F 0 of x has to be sigma of a of 0 comma r equal to 1 to infinity x raised to r. Here we have the first term as a00 plus next term is a01 x raised to 1 plus next term is a02 x square and so on. So, but here we are talking about selecting one object from 0 objects. This should be 0, this should be 0 and so on, right. So, all these things will be considered 0. So, that means we will define a0 comma r where r greater than 0 as 0. We will define this way, right. So, therefore, this will not be, this f0 of x will be just a00 which is 1, right. So, we note that f0 of x is just 1. Now, so in our recurrence relation we told that this a of n comma r equal to a of n minus 1 comma r plus a of n comma r minus 1. This is valid for r greater than or equal to 1 only. Also we will make that this is valid for n greater than or equal to 1 only, because otherwise we will have to again think about what will be a minus 1 r, right. So, we will think that n is at least 1, so that we can get this thing. So, now what we are going to do is, so from this recurrence relation, so I will again write it once again, because this is, so what, okay, this recurrence relation, so this is the thing, right. I will sum it from r equal to, this is, remember this recurrence relation itself is valid only from r equal to 1 onwards, r equal to 1 to infinity, I will sum. So, this will become again r equal to 1 to infinity, this side also will r equal to 1 to infinity. Then what is happening? So, this is, as we have defined, if we had summed from r equal to 0 to infinity, this, sorry, so I am sorry. So, what we have to do is each term should be multiplied by, so I will make it clearer. So, into, okay, fine. So, before summing this, what I should do is, so we write like this. So, this is equal to this. Now, I will go back again once again. A n comma r is equal to a n comma r minus 1 plus a n minus 1 comma r. This is the equation. Now, we can multiply this by x raised to r, that is okay, right. Here also we multiply by x raised to r, here also we multiply by x raised to r. Now, we sum r equal to 1 to infinity, and so this should be multiplied by r equal to 1 to infinity, and this should be multiplied from r, sorry, summed from r equal to 1 to infinity. So, if we had summed, if the sum was from r equal to 0 to infinity, that would be just fn of x, but then we are taking from r equal to 1 to infinity. So, we get fn of x minus the first term a n 0. This is equal to, here also the same thing, just that we have to do some adjustment here. This is r minus 1, but it is x raised to r. So, what we can do is, we can change this to r minus 1 and take an x out here. I can take an x out here. So, x into x raised to r minus 1, right. Now, this variable can be changed. This is r minus 1, let us call it r dash, right. So, this will also become r dash, and now we can say that this r dash goes from 0 to infinity, because r goes from 1 to infinity, then r dash equal to r minus 1 will go from 0 to infinity. So, this is x into r dash equal to 0 to infinity a of n comma r dash into x raised to r dash, which is essentially the generating function f n x, right. And what about this term? This term is just r equal to 1 to infinity a n minus 1 r x raised to r, and you know, if you had summed from r equal to 0 to infinity, this would have become just f n minus 1 of x, right, and minus a, this would become minus a n minus 1 0, because the first term should be minused. So, but a n 0 is 1, a n minus 1 0 is also 1, right. So, we are, remember, we are only talking about this entire thing, n is assumed to be at least 1. So, a n minus 1 0, a n minus 1 0 is a 0 0, that is all, the worst case. A f n minus 1 0 is already defined, you know, that is just 1 in that if n equal to 1. So, now we can rearrange the terms and get that 1 minus x into f n of x equal to f n minus 1 of x. So, that is f n of x is equal to 1 minus x to the power minus 1 into f n minus 1 of x, or we can write it as this way also, f n minus 1 x by 1 minus x. Now, you see, you keep unrolling it, f n of x is equal to f n minus 1 of x is equal to f n minus 2 of x by 1 minus x square and so on. Now, when it goes to 0, this will become f 0 of x, that means n times we have done it. So, this is the answer. But then this f 0 of x is just 1, as we have seen, 1 by 1 minus x raised to n. So, we get f n of x is equal to 1 by 1 minus x whole raised to n. So, this is the generating function. Now, if you want to find a n comma r, we look for the coefficient of x raised to n in the expansion of f n of x. This will be f n of r. What will be that? Because f n of x is equal to 1 by 1 minus x raised to n power minus n. We know the coefficient is minus n, choose r, which is what? R plus n minus 1, choose r. This we already know the answer, but we can derive it this way also using the method of generating functions. So, that is the derivation for this thing. This is a slightly different thing. So, in the sense that we had a sequence corresponding to each n, right, for a fixed n, and then we had a sequence corresponding to that, right, and corresponding to that we could get one generating function f n of x. So, we were not dealing with just one generating function, we had a family of generating functions here. Therefore, this example was interesting, though the problem was already familiar to us and we knew the answer already. And now we will take a very similar example, and we already know all these things. For instance, n choose r. What is the recurrence relation known for that? The n choose r being the number of ways of selecting r objects out of n without allowing repetition this time. It is more familiar. So, n choose r is equal to what? Same argument, if you remember. So, you can select one object, and then that will make the selection like this. Or you can decide not to take it at all. So, that means you have to select from n minus 1 objects r objects. This is the recurrence relation. This definitely works for n greater than or equal to 1, but we have to be careful. For instance, n equal to, so this, okay, for instance, we are only talking about, so we already discussed the entire thing of, right, we had very elaborately discussed when we are allowing r equal to negative and so on. But yeah, here let us just remind you, all n choose 0 is always equal to 1. So, if you consider n choose r, where r is bigger than n, then we will get this is equal to 0, right. For n choose r, when r is bigger than n, we will get this is equal to 0, right. So, now, so what about this recurrence relation? This recurrence relation, so is it for instance, n choose 1. So, we want to take one object out of n. So, that means you can select that object. So, we want to select r minus 0 objects out of n minus 1 objects. This is one. Another way of doing it is you can decide not to select it, right. So, you want to select one object from n minus 1 object. This works fine. But if you put r equal to 1, the problem is we have negative n minus 1 choose minus 1 here. So, this recurrence relation is not valid, right, because we do not have any counting interpretation of n minus 1 choose minus 1, etc. We had discussed it earlier. So, therefore, we will only say that this recurrence relation is valid for r greater than or equal to 1. And similarly, so we can say that for n equal to 0, out of 0 objects we want to select r objects. So, then this recurrence relation will not be, because we will be talking about selecting out of minus 1 object something. So, that also we are not assuming, we will assume that n is greater than or equal to 1, right. So, if n equal to 1, that is fine, because we want to select r objects out of 1 objects. So, we will be thinking about selecting 0 objects out of 0 and so on. So, for instance, if it was bigger, this should be 0, r is bigger than 1, then it will be 0. So, what happens is, so we will be taking something bigger here from 0 objects, and then both are zeros, right. On the other hand, if r was equal to 1, then we will be talking about selecting 0 choose 0. So, this will be 1, 0 choose 0 here, and this will be 0 choose 1, which is 0, which is also correct. We have verified it before again. So, when in the case of n equal to, so n 1 choose 0, that should be 1, right. So, that means 0 choose, sorry, r is not 0, r is 1 maximum, right. So, therefore, that is fine. So, we are assuming that r is greater than or equal to 1 and n is greater than or equal to 1. You should verify it very carefully whether we can make these assumptions. And then so now that we have the recurrence relation, and we will define some generating functions for that. So because we need, like we did in the earlier case, in the last case, we will define sequences like this, fix an n, and then we can define the sequence n choose 0, n choose 1, this is a sequence, right, n choose 2, n choose 3, n choose, this is one sequence, and the generating function fn of x is defined to be sigma r equal to 0 to infinity n choose r x raised to r. Okay, this is familiar. So, we know this thing, this is 1 plus x, right, but we will derive it. So, you will say that why you are doing this thing, but it is just to show how you use the recurrent use our generating function method some to derive the generating function. See, which you already know by binomial theorem, this is equal to 1 plus x raised to n, right, 1 plus x raised to n, but we will get this thing by a different method just to illustrate. So, now just let us, so I will do one more thing, I will see what is, because this recurrence relation was valid for n greater than or equal to 1. So, I will see what is f0 of x. f0 of x will be n choose 0 plus, sorry, n 0 choose 0 plus 0 choose 1 x and so on, 0 choose 2 x square, but these are all zeros, right, therefore they will not be there. This is just 0 choose 0, and which is just equal to 1 as before, right, f0 of x will be 1. Now, let us look at our recurrence relation once again. It is n choose r equal to n minus 1 choose r minus 1 plus n minus 1 choose r. Now, we can multiply by x raised to r everywhere, that is not a problem. Then after that we sum. Here we sum only from r equal to 1 to infinity, because the recurrence relation itself is valid only for r greater than or equal to 1. We cannot sum from r equal to 0 to, because when r equal to 0, this equation we wrote is not correct. So, this will also go from r equal to 1 to infinity, and here this also will go from r equal to 1 to infinity. Okay. Now, what we do is, this one, if we had sum from r equal to 0 to infinity, we would just get fn of x, but then we just missed the first term. So, we can write this as fn of x minus, the first term is what, n choose 0, x raised to 0, that is not necessary, n choose 0, right. So, this is equal to what, here, because here this is r minus 1, here is r. So, what we do is we pull out one x from here and make it r minus 1. So, that means we will get an x here, one x will come out, one x will come out. So, now we can change the variable. So, let us call it r dash now, r minus 1 is called r dash. So, this will be called r dash. So, we can use a different color to indicate that. Yeah, you can call it r dash, right. So, this x was pulled out. Okay. Now, we see r dash is going from r dash is going from r dash is going from 0 to infinity, because r was going from 1 to infinity, r dash being r minus 1, that will go from 0 to infinity. So, this is perfect. So, r dash is 0 to infinity and n minus 1 choose r dash into x raised to r dash. That we know this x is anyway copied, and this will become f n minus 1 of x, right, because this full summation is there, r dash equal to 0 to infinity. Here we have n minus 1 choose r into x raised to r, and that is going from 1 to infinity. If r is going from 0 to infinity, we could have just wrote f n minus 1 of x here, but then here we have to minus the first term because we did not take the first term here. So, that is n minus 1 choose 0 into x raised to 0, anyway that is 1. But n choose 0 and n minus 1 choose 0 both are 1. It's not that n was at least 1. So, therefore, n choose 0, this can be in the worst case n minus 1 0 can be 0 choose 0, therefore, we have it, right, both are 1. So, we cancel it off, it is not necessary. So, now rearranging, so we see, sorry, no need to rearrange, we can combine x f n minus 1 x plus this one. So, that is f n of x equal to 1 plus x into f n minus 1 of x. Now, we can keep on unrolling, this will be 1 plus x into f n minus 2 of x, sorry, square, and so on. So, finally, this will become 1 plus x raised to n into f 0 of x, which is just 1 plus x whole raised to n. This is what the binomial theorem, from binomial theorem you already knew that it should be 1 plus x raised to n, but we can get it in a roundabout way like this. So, just for illustrating the technique. Now, we want to consider one more example which is slightly different. Let us look at a system of recurrence relations. We have a sequence A0, A1, A2, A3, A4, etc., and another sequence B1, B2, B3, B4, etc., and we are given some initial conditions also, A0 equal to 1, B0 equal to 0. So, how will you deal with this kind of a setup? So, I will copy this here, a n plus 1 equal to 2 times a n plus b n, a n plus 1 equal to 2 times a n plus b n, and b n plus 1 equal to a n plus b n. And this is valid for say n equal to 0 onwards. So, both equations are true for n greater than equal to 0 onwards. So, but of course, this starts with 1. So, what we can do is we can define two generating functions. One is, say, for corresponding to this we can define a generating function a of x. A of x can be defined as sigma r equal to 0 to infinity a r into x raised to r. So, that is like a0 plus a1x plus a2x square plus so on, a n x raised to n and so on. Similarly, we can define b of x, which is sigma r equal to 0 to infinity b r x raised to r. Now, we want to figure out what is this a of x and b of x. So, let us copy these two recurrence relations once again, a n plus 1 equal to a n plus 1 equal to 2 a n plus b n and b n plus 1 equal to, okay, from this thing what do we get, let us see. So, what we can do is we sum this from n equal to 0 to infinity. N equal to 0 to infinity. So sorry, before that we have to multiply this by x raised to n plus 1. So this here also I will multiply by x raised to n plus 1, 6 raised to n plus 1. This is correct because we multiplied every term by x raised to n plus 1. Now we sum from n equal to 0 to infinity. So when you sum it from 0 to infinity, so note that this is n plus 1, therefore a1 x raised to 1, a2 x raised to 2 and so on is the. So this is not really our a of x, this is only a of x minus a0 into x raised to 0, that is a0. a0 is not to be 1, as we have, if we are given that a0 is 1, we can write it a of x minus 1. This is on the other hand, so this also will sum, right. So this will be n equal to 0 to infinity, this will also from n equal to 0 to infinity. Here we can definitely take out, say this, we can, this x we can take out. So that means we will just keep x raised to n here, right. So that means we have x into a of x, sorry 2x into a of x here. This 2 comes out, x also comes out. So then is a n and x raised to n here, and n is going from 0 to infinity, therefore that is a of x into 2x. Similarly here x comes out, say this will remove and put an x here, and then from n equal to 0 to infinity, bn into x raised to n is b of x, this x into b of x. So we get an equation like this. So this is what we get. A of x minus 1 is equal to, so this is my first equation, a of x minus 1 is equal to 2x into a of x plus x into b of x. Secondly, so maybe secondly we can use the recurrence relation, the other part of the recurrence relation, bn plus 1 is equal to an plus bn. Here also we can multiply by x raised to n plus 1 first, x raised to n plus 1 first, x raised to n plus 1 first, and then now sum it from n equal to 0 to infinity everywhere. What do we get? This is, because it is only going from n equal to 0 to infinity, means n plus 1 goes from 1 to infinity. So this is not really bx, it is only b of x minus b0, which is 0, we know, right, b of x minus 0 equal to, here what happens, x comes out, so this x into, then a n into x raised to n will come and n will go from 0 to infinity, therefore that is a of x, plus this is x comes out, x into b of x will come. So now we have two simultaneous equations in a of x and b of x. This I can try to rearrange. What happens is this will be x into a of x plus x minus 1 into b of x, x into a of x plus x minus 1 into b of x equal to 0. This is what this will happen. This I just took x into a of x here, x, and this b of x is brought here, x minus 1 into b of x is equal to 0. Here this one also I can rearrange, I can take ax terms to this, that is 1 minus 2x into ax minus xbx, 1 minus 2x into ax minus xbx is equal to, so I continue in the next class.